Hey guys, the planer here. In this video we're going to discuss a little bit the basic principle of curvature. We're not going too deep into mathematical stuff, and we're not discussing everything that mathematicians have come up with, because there are infinite amounts of definitions for curvature. It's just trying to describe reality, and you will never be 100% correct. And first, I think from science standpoint, they had the one example with the curvature circle, where the one divided by the radius of this curvature circle is the curvature. And then we have curvature with arc length next, I think, and so on. So there are multiple different definitions for curvature, and every definition can be used. It's just definitions are like tools, and for certain things you will want to use different tools. And some tools may be better, some less good, but the same with tools and definitions. There can be an infinite amount of definitions. Some definitions are better, some not, but yeah. And we're just going to look into the basic principle, as I said, and after we go through some examples and discuss this a little bit, I want to show you the sphere method that I was coming up with to describe the principle that we discussed in the last video, how curvature gets affected on the globe. The sphere method obviously is made for getting better feeling for the curvature on a globe Earth model. And yeah, and after that I think we go into the real meat of going further with plane Earth and globe Earth model comparisons. So now the basics. Of course there can be many people saying different things, but for now, I would say curvature is the definition of how much something curves. Amount of definitions are endless, or is endless. It's, yeah, you can describe something in infinite amount of ways. So, there is no right and wrong here. There's just a more right and a more wrong, but no one will be 100% correct with anything. That's not possible by us. We can only describe so much. We can never be 100% reality with the constructs that we try to describe curvature with. So yeah. Yeah, let's go. Yeah, and now that the definition itself, the only thing it should fulfill, I mean, honestly, it doesn't really matter if it's fulfilling this. Honestly, it doesn't matter. But if you want to use it, it would be good if different form arcs have different values for curvature. Otherwise, your curvature value will be useless, kind of. Depends for what you need it, but usually you want to have different values for different arcs. Yeah, that's, I think, the most important thing. Of course, there can be thousands of important things, but honestly, that's not really the topic today. So yeah, let's go on. So now the common definition of curvature. Yeah, it's high when it's sharper normally, and it's low when it's less sharp. But you can also invert it. It doesn't matter. It's just for you. If you want to, you know, invert it, then it's your choice, and you just need to adjust your other stuff too, because normally people do this with sharper higher value and less sharp lower value, but it's your choice, honestly, as long as you have the things you need to describe a curve. It doesn't matter how the values are exactly. So if they're inverted or not, it doesn't matter. When you think of it, when you apply it on the other formulas that you want to use. So when we go to the common types, there is two types, the absolute curvature and the relative curvature. Normally, I think in science, so-called people, I think, only use absolute curvature. Relative curvature is just because I found it interesting that you can also, you know, describe relative curvature. I mean, for some it's obvious, but I wanted to add it too, where you have, of course, the same arcs just scaled down, and in relative curvature, when these arcs are the same, they just stay the same curvature. And for absolute curvature, of course, if it's smaller, it gets more curvature value, which is obvious and the most common used thing. I don't know where you should use relative curvature, but yeah, it's worth mentioning. So now to the vertex point of an arc, and that's my definition for this video in there. For a vertex point, it doesn't really matter. There may be many other definitions for vertex points, but for this video we're using this definition, and that's okay. And we're using the point from which the arc is symmetrical. So yeah, there you can see the arc is symmetrical, and when you use there half of it, it's asymmetrical, and there also asymmetrical. And you see, the thing is, the more it goes in direction of a sphere, the less asymmetrical the halves get. But yeah, there you see symmetrical, and the halves of them are not symmetrical. So in these arcs, you have only one vertex point by this definition. So now for the curvature circle, there may be other definitions for the curvature circle. In this video I will use this definition. It doesn't really matter as long as we're consistent with it, and I just want to discuss the basic principle. I don't need some deep mathematical calculations or something. Just need to talk about the principle, and that's enough for that. Yeah, we get the vertex point, and from that we draw a sphere through, and we scale up the sphere so that as many points as possible align with the arc without overlapping there. So we look how big the circle can be when it goes symmetrical through the arc and still fit the arc. And yeah, then we get the curvature circle and its radius by this definition we use in this video. So now for discussing these principles, we start with methods. The first method is the observer method. It's not mathematical in itself, but it has the same principles. So if there small curvature, it's less curvy, small angle change per length, and more flat arc. Yeah, and high curvature, it's more curvy, big angle change. You see the angle changes very fast, and more sharp arc. Yeah, that's just obvious feeling, knowing. There's no need to describe that further. So, and that's I think was one of the first definitions of curvature, as far as I know. There you have the curvature circle, and then you divide 1 divided by, you make 1 divided by r, and that's the curvature, the radius of the curvature circle. And when the arc is sharp, then you have a small curvature circle and you get a small radius. Means the curvature value will be high, because 1 divided by something small will be something high normally. And yeah, small radius, of course. And then we have less sharp arc, and we have big radius. And 1 divided by something big is small, so we have small curvature. Very interesting. And yeah, it fulfills the normal things it must fulfill, and yeah, for some cases it's helpful. So now we go to the arc method. It may be a little bit different than normally, but it may have a lot in common with the normal arc methods. It's having different sizes, the angle difference, the arc length, and the dy and the dx. dy, dx. And there are also dy, dx. You see. And yeah, we have there again, we have sharp arc, means high curvature. How do we get it? Angle difference divided by arc length. So we have a big angle difference, as we can see, and relative small arc length, and that means big angle difference divided by a small arc length is big. That means this is a big curvature. Then we have there a small angle difference, as we can see, and big arc length. So small divided by big is small curvature. And then we can do there angle difference again, so we can control. We have this, that is not there in this example, but let's try this. So we have angle difference, and we have small dx. So big angle difference, small dx. So big divided by small is very, very big. So we have something very, very big. And then we have small angle difference, big dx. So something small to something big is small. Honestly, I didn't experiment too much with it, so it could be that you cannot mix these two together. And the relative is of course the relation of the x and the y. Then you get some kind of relative curvature. I think that's all. It's very basic. And it's not necessary to go too deep, because it's not needed for this video. But yeah, let's go on. So now we get to the triangle method, and the triangle method is should be, yeah, it's a relative, it's relative curvature. It's the relation of the arc sizes around the arc. There we have alpha, and there is high curvature, and there we got, wait, damn it. So, yeah, small beta, and we got, I think, yeah, a relatively big alpha, and that's high curvature, and with the more flat triangle we have a smaller alpha, so we have smaller curvature, so we can say directly it's alpha, and I'm pretty sure it's not exchangeable, so if you take one of those you will need to take one of them, but you can't mix it. I think I didn't try it. Honestly, that's not the point of the video. Yeah, H arc, W arc is the next. That's the same basically, like dy and dx. Just the interesting thing is that when the arc swaps axis, then the H and the W swap too, because in the arc method we had to switch it manually, dy and dx. When the axis switches, they switch too. But in this case, these two switch automatically. So you could, I think, this one you could also calculate with W and H. Wait, what would that be? Yeah, it would be the W angle difference divided by W, I think, yeah. So yeah, it's just experimenting this video. It's not having a goal or something, just talking about the basic principles and exploring a little bit the possibilities, not more, not less. And of course, with beta, we have relatively small when it gets sharper, and relatively big when it gets less sharp, the arc, and then we get the big beta, and that's why, like the radius of the curvature circle, 1 divided by beta, small beta, we have high curvature, big beta, small curvature. So we have this as well, and yeah, it's kind of interesting. It's nice to play a little bit around. It's to get the feeling for these things. Of course, we don't not high mathematics or something, but that's not necessary. And yeah, let's go on. Now we're going to the last part, the sphere method, and that's kind of a recap, maybe from the last video, where we discussed basically the more you see, the more you can see of a sphere, the more curvature you will see. And yeah, I don't know, there seems the color to be as white as the background, so I'm sorry. So we see there is alpha, beta, gamma, and gamma has a high angle, beta has a medium angle, alpha has a small angle, and the small, in the alpha you see a small percent of the sphere, and that's in the imagery. Like in this camera, you see the alpha, a small angle, and a small percent of the sphere, and you see small curvature. Then you see a bigger part of the sphere, and you see the angle beta, a medium angle, medium percent of the sphere. You see medium curvature, so called. And then gamma, high angle. In the third camera you're further away and you see more, or you have a ultra wide fish lens or something, and then you have a high angle with high percent of what you see of the sphere, and then you have high curvature. of course, when you see the whole sphere, there can't be, or half of the sphere, better called, there is no increase of curvature, obviously. Yeah, and you have high angle is high percent. The more you see percent, the higher the curvature angle. They are in the sphere methods, they're one and the same basically. You can say what you see is curvature. The more you see, the more curvature you see. Relative curvature, the angle, yeah. That's because we have no other size, so it doesn't matter if how big the sphere is. With an angle, we always get only the relative curvature of a sphere. Percent the same. And absolute curvature when we get the angle, and percent in relation to its radius. Yeah, and relative curvature, angular percent of the sphere. Yeah, that's the same again. And yeah, that's just a little bit of playing around and, you know, seeing like the things that we've discussed about a sphere, a big sphere, a globe Earth model, where how to really get a grasp how curvature on a globe Earth model really works. And yeah, that's I found it very interesting. Theoretically, you could, you know, the sphere method, you could combine it with the circle method, but that's just crazy. Honestly, I don't think it's really fun to do that. I think it's, yeah, I don't know what to think about that, but yeah, I find it very interesting. I like the sphere method. Shows us how it's really like the more you see on the sphere, the more curvature you see too on the horizon. That's very interesting. And yeah, in the next video, I hope I get more into the meat of things. And I think maybe there will come another video about a basic video about lenses. And then I think it goes on to, you know, we go on in our investigation of the globe and plane Earth, and yeah, we see what we can find out with the data we have and what we established already. So yeah, have a nice day.